All right, let's get right into it. We're going to be looking at a scientific paper that's uncovered a material with some, well, truly remarkable, almost sci-fi level abilities. It's a story all about turning wasted energy into something incredibly useful.
But first, let's start with a really basic question. When we burn fuel in a power plant, or heck, even just run our computers, where does all that energy actually end up? Now, you might think it all gets turned into electricity or processing power, but that's not really the whole story.
The kind of surprising truth is that a massive chunk of it is just lost. It's lost as waste heat. It's radiating away from everything, our laptops, our cars, those huge industrial smokestacks. Honestly, it's one of the biggest hidden drains on our entire energy system.
So how are scientists trying to plug this massive energy leak? Well, here's our roadmap for this explainer. We're going to start by getting a feel for just how much heat we're wasting. Then we'll get into the pretty wild idea of making electricity from a temperature difference. We'll meet our star of the show, a crystal called CADPS3, see how a digital microscope revealed its secrets, discover its two incredible talents, and finally, look at its path to actually powering our future.
Okay, first things first. Let's really get a handle on just how big of a problem this waste heat thing actually is.
The researchers behind this paper put it perfectly. This is not a small issue. Significant quantities of heat are just constantly being thrown away by, well, pretty much everything in our modern world. If we could find a way to capture and reuse even a little bit of that, it would be a total game changer for energy efficiency.
So how in the world could we possibly get that lost energy back? This brings us to a really fascinating corner of material science.
The key is something called a thermoelectron material. So imagine you have this special kind of tile. If you make one side of it hot and the other side cool, this material can actually generate electricity right from that temperature difference. There are no moving parts, no turbines, it's just solid-state physics doing its thing. This is the tech that could literally eat all that waste heat.
Now, scientists have been on the hunt for the perfect thermoelectric material for decades, and this new research shines a really bright spotlight on a very promising, if kind of little-known, candidate.
So let's meet our hero, cadmium phosphorus trisulfide, or let's just call it CDPS3. It's this layered crystal, and based on its structure, it looked like it should be pretty good for this thermoelectric stuff. But as the paper points out, nobody had really done the deep dive. No one had done the fundamental analysis to see if it was actually any good. Its real potential was a complete mystery.
To solve this mystery, the researchers didn't start in a chemistry lab with beakers and burners. Nope, they started with a supercomputer, using something you could call a digital microscope.
They used this incredibly powerful technique called a first principles calculation. And here's the really mind-blowing part. This lets them predict everything about a material, how it conducts electricity, how it reacts to light, all without ever touching a physical sample. It's all done in a simulation, atom by atom, based on the fundamental laws of quantum mechanics.
I mean, it's an unbelievably powerful way to do science. Think about it. It's like having the ultimate instruction manual for how atoms are supposed to behave. This lets you build and test countless materials right there inside a computer before you ever commit time and money to making them in the real world.
So when they put CDPS3 through this digital test, the results were, well, they were pretty astonishing. It turns out this material isn't just a one-trick pony. It's a superstar with two very distinct and very powerful talents.
Okay, talent number one is exactly what they were hoping to find. It is excellent at turning heat into electricity. But talent number two was this incredible bonus. It's also superb at absorbing a very specific kind of light, invisible ultraviolet or UV light. This is a powerful one-two punch of abilities that you just don't see very often in a single material.
All right, for that first talent, let's talk numbers for a sec. In the world of thermoelectrics, there's this key performance number called the figure of merit, or ZT. Just think of it as its efficiency rating. Now, to go from being a cool lab experiment to something you can actually use, you need a ZT of about 1.0. And guess what the simulations showed? They showed CDPS3 hits that gold standard right on the money. This isn't just kind of neat, it's a huge green light for developing real-world tech.
And this chart? This perfectly shows off its second talent. Look at that bar on the left. For visible light, the kind our eyes see, the absorption is super low. The material is practically see-through. But now look at the bar on the right. The second you hit it with that high-energy ultraviolet light, boom, its absorption goes through the roof. It basically acts like a specialized sponge, soaking up all the UV light while letting everything else pass right on by. This super advanced computer model also let the researchers create a much more accurate blueprint of the material. They were able to pin down its band gap, which is a fundamental property that basically dictates how it interacts with energy. Think of it as the minimum energy you need to zap an electron and get it to conduct electricity. Before this, the estimates were kind of all over the map, but this study nailed it at 3.1 electron volts. Having that precise number is like finding a key piece of the puzzle, and it's absolutely essential for engineers who want to actually design devices with this stuff.
Okay, so we have this material with two amazing talents, and it's all backed up by some really solid computational evidence. What does this all mean for the future? What's the path from this digital discovery to actual real-world power?
Well, the applications come straight from its two talents. First, you can use it for waste heat recovery, creating little devices that can just sit on factory exhausts, or data centers, or even car engines, and just scavenge that heat, turning it back into useful electricity. And second, you can use its special light-absorbing trick to build incredibly sensitive UV sensors for things like water purification systems, or maybe even early warning fire detectors that can spot the unique UV signature of a flame.
So what's the big takeaway here? Why does this all matter? Well, for one, it's a direct way to boost our overall energy efficiency. It could create brand new ways to power small devices. It opens up the door for all sorts of advanced UV sensors and other high-tech electronics. And maybe, just maybe, the most important thing is that this study gives us a roadmap. It's a successful proof of concept for how to use these powerful computer tools to discover and design even better materials in the future.
And that really leaves us with a fascinating final thought. This research gives us a glimpse of a potential future that's unlocked by materials like CDPS3. So just think about it. What if? What if every hot surface we create, from the back of your laptop to the top of a giant factory smokestack, could stop just wasting all that energy and instead become its own clean,